Good evening and a warm welcome to the GSPL webinar series on decoding steel and healthcare infrastructure. May I now introduce you to the moderator and speakers for today. Our keynote address is Mr. V.R. Sharma. Mr. Vidya Ratan Sharma is a leading technocrat with more than 37 years of experience in steel, power, cement, and mining industry. At present, he is working as the managing director of Jindal Steel and Power Limited, one of India's leading conglomerates with interest in steel, power, mining, and infrastructure. He joined GSPL in June 2019. During his tenure, GSPL has undertaken several steps to transform itself as has shown excellent performance on all fronts. This includes an impressive higher production and sales and turnover during COVID-19, induced economically challenging period. Under his leadership, GSPL recorded its highest sales in the quarter one of for the financial year 21. Up next, the moderator for the day, Mr. Ruchir Panwal, Principal Architect, E3 plus A Architects. Mr. Ruchir has an international professional experience in design and planning of hotels, software technology facilities, airports, healthcare facilities, signature buildings, and sports facilities. He has been the group head for the design of super specialty, multi-specialty hospitals, integrated healthcare complexes, medicities, airplane hangars, MRO facilities, cargo terminals and air traffic control facilities, software technology facilities, cricket and sports stadiums, SEZ and industrial parks. Now our speakers, Mr. Douglas P. Gonzalez, partner Lera Consulting Engineers. Doug has a Master of Science from Cornell University and a Bachelor of Engineering from the Cooper Union in New York City. Mr. Douglas P. Gonzalez is a partner at Lera Consulting Structural Engineers. With the firm since 1991, Doug has led Lera's efforts in healthcare, science, and adaptive reuse and renovation work, and has considerable expertise in designing cultural, civic, and other institutional facilities. In his role as a quality assurance manager for Lera, he oversees Lera's quality control and knowledge management processes and programs. Mr. Doug is an active leader with many industry organizations. Up next, Mr. Gokul Kamath, Senior Associate, Lera Consulting Structural Engineers. Mr. Kamath has done his MS in Structural Engineering from Virginia Tech, USA, and BE Civil Engineering. He has also worked in projects like office buildings, hotel, residential projects from Mumbai, Malaysia, and Kuwait. He is a member of American Concrete Institute India and Civil Engineering Association, Mumbai. Up next, Mr. Subrat Panda, VP Business Head Structural, Sales and Marketing. Mr. Subrat Panda is currently working as a business unit head for GSPL and has been working for over 28 years in the steel industry. He's an electrical engineer, started his career with sales when he worked with central marketing organizations. He was a branch manager in Mumbai where he decided to move to GSPL after working for about 20 years. He's an avid reader and a fitness freak. Up next is Mr. Hiten Mahindra, Director, Mahindra Consultants Limited, a ME Civil from University of Michigan and a BE Civil from Manipal University of Technology. Mr. Hiten is currently working as a Director of Mahindra Consultants. He has over 34 years of experience and has worked on various national and international projects involving detailed structural engineering, conceptual planning, structural assessment studies, etc. He is a member of PEATA, Bombay, member of the Institute of Engineers India, and many more professional bodies. Mr. Mahindra has many awards on his name and was the chairman of the Steel Day 2019 Experts Committee. Before I hand it over to Mr. Sharma, requesting all the attendees to please participate in the poll and do write the name of the speaker whom you would like to address the questions to during the Q&A session. Also, do subscribe to our YouTube channel, STS TV, where we are live now and you can get steel construction updates. Over to you, Mr. Sharma.
Yeah, thank you very much. Good afternoon, ladies and gentlemen, my colleagues, the technocrats, the consultants, those who are attending today's webinar. So I welcome all of you in this particular webinar. I'm sure this series will definitely be useful to disseminate knowledge to each other and which can be utilized for the upliftment of mankind. And that's the main purpose. Of course, business is paramount for anyone. But yes, when we discuss, when we interact, then finally the business do come. So we have to find out the technological solutions for many things, and will try to complete during this complete webinar, and also in the series to come in times to come. As the title is, we are today going to discuss what is going to happen in terms of uh, infrastructure growth, in terms of hospital industry, in terms of oxygen plants, and so on and so on. We have a lot many plants available in the country where they have contributed a lot to the hospital industry in last so many years. There are so many hospitals which are built through porta cabins, which are built through PEBs, that is pre-engineered buildings, and finally which are built through the steel structure in for high-rise hospitals. A few of the hospitals in NCR and few of the hospitals in Pune as well as in Bangalore are built through structural steel. And this is a wonderful technology which not only saves time, but it is cost effective also. And people are working day in, day night as to how to develop different design for the hospital industry as a whole. We have seen during last pandemic, there was a shortage of oxygen in India, especially. There was a shortage of oxygen, and in some other parts of the world also. But India, the pandemic was very severe, and we found that the shortage was to the tune of about 1,000 tons of oxygen every day. And the problem was basically because of overall transportation issues. So we have seen that the cryogenic storage tanks is the answer, and this is what JSPL is now working very seriously, how to develop the cryogenic storage tanks for the nation. We have already done two tanks for the cryogenic applications, and I'm sure in times to come we'll be developing this particular product regularly. The primary health centers a part of the country are Delhi alone has more than 70 porta for the so-called we call them mohalla clinic. So these mohalla clinic declared by the Delhi government. I'm thankful to Mr. Kejriwal who has started this particular concept, and we have found that many PEs type of regional building and porta cabins are used for the primary health care and primary health centers, not only in day-to-day life, but it is also giving a great amount of flexibility by making it a portable hospital or portable health, and they are mounted on a 40 feet container and 40 feet trailer, and then people are transporting these moving hospitals or moving primary health care center from one location to another location. Now the time has come to utilize steel in the hospital buildings, which will be cost effective and which will be faster also. We have seen that Government of India has declared so many stimulus packages, and one of the packages defined that more and more hospitals are required to be built in the country, and that too in a span of next 6 to 8 months time. If that want to make it happen, and the only answer is steel buildings, and that is fabricated buildings as well as the steel structure rolled buildings. So these are the areas where we have to work together with the hospital industry. Side by side, we have to install the oxygen plants, and the best of the best oxygen plants in a multiple of modules. They are available today in the containers, and also these are to be installed on a steel structure building, so that one can save the space in terms of overall effectivity. The containers which are fitted with the oxygen plant generation, they can come on the first
I believe there is some network issue. Mr. Sharma, we lost you just while closer to the 30 seconds back. We lost you. There was some, I think, network issue.
So you can please unmute yourself.
Hello, am I audible now?
Yes, sir. We can hear you now.
Sorry, there was some, I think, connection issue. I'm sorry for that. Sorry for the inconvenience. So I was talking that we have more than 700 districts and the large towns in the country. And all these 700 large towns, as per the latest report available, they need at least 2,000 small hospitals. Small hospital means a 10-bed or 20-bed of hospital, which is equipped with all of the facilities in terms of infrastructure, in terms of utilities, in terms of oxygen plant, which is fitted in a container, which can give at least oxygen to maybe to 50 or 60 people 24/7. So this is only possible when we install all these facilities on a steel structure building. It is impossible to complete the task within the next 6 to 8 months time if we start manufacturing or we start constructing the hospital through RCC route or through any other route. So whether it is brickwork or RCC route, the best is to produce these hospitals or to manufacture these hospitals or to establish this facility through steel structure buildings. If you see the other area which is coming up very fast in the country, that is hotel industry. There are more than 57 hotels on the Aero City near Terminal 3 of New Delhi. All these hotels are built through basically through steel structure, and even walls are through the framing business. So the framing technology is picking up very fast in the country. Again, the galvanized and the color coated material is going to be used in the framing business. Many of the companies like FrameCAD and some of the Chinese companies, some of the companies like Pinnacle in Canada, they have come and they have put up their shops in the country to supply the galvanized frames for the walls and the partition walls. So this is a business which is picking up very fast. There is a great amount of career, there is a great amount of opportunity for the professionals, for the consultants, and for the contracting companies to build hospitals, primary healthcare centers, small hospitals, and also large hospitals through the steel structure building. So that's all from my side. I'll hear all of you in case of any question. I'm available throughout the session. Thank you very much.
Thank you so much, Mr. Sharma. Thanks for such an insightful keynote. Now, I will hand over the proceedings for today's program to Mr. Ruchir Panwar, who is also the moderator for today's session. Ruchirji, over to you, please.
Thank you, Avneet, and welcome to all the panelists. Healthcare is a very critical aspect for any society, and the development and stability of a society is basically judged on the amount of healthcare facilities and doctors per capita. So India, unfortunately, has a dubious category. We have a lot of hospitals. We do have a lot of trained and very well-trained doctors. Unfortunately, they don't get the right facilities. So even though there are in number and quantity a lot of hospitals developed, but it's appalling to walk into one and see that you have a high wall split in an operation theater. And that's called a specialty, super specialty or multi-specialty hospital facility. So being an architect and having to fight against many mindsets of healthcare developers and healthcare management companies such as Wockhardt and Fortis and Apollo, they have matured quite a bit. and international healthcare standards have come into the Indian healthcare development, facility development industry. However, there is still no legal framework which is something which is mandatory to be followed. So we always go back to the National Building Code or the local building bylaws. And all buildings, be it healthcare, be it hospitality, be it anything, get subjected to these generic and very general laws. So I think it's up to us as professionals to be conscientious on all sides and all the stakeholders for a project to actually make a basic minimum program for safety, security, well-being, and medical standards, which have to be adhered to and which should be designed and planned into our design program at the inset itself. Now, I would like all of you to just share any experiences. Anyone can take this, and we can start with any of the panelists who have had a similar experience in the country or elsewhere, where they've faced the challenges of not having proper planning guidelines in place, which, from the local authorities or the mandatory governing bodies which govern the development and setting up of healthcare facilities. So whatever were the challenges, and then we'll take it from there, and we'll try and slowly come to a conclusive closure as to what we can do at our end, rather than always expect the government to do something and then go back home and then rest easy, and wait for the government to come up with something. So we'll have to probably, as leaders of the industry, we are at a position where we can set the standards, we can set the ball rolling by making the first steps for others to follow in. So that'll be my conclusion, intent to conclude on the whole panel discussion. So I start with the first question about whatever were the challenges, which are really basic. So whatever comes to your mind, gentlemen, please take over, whoever wants to go ahead first.
Richardji, we'll start with a small presentation. We have some interesting presentation from Doug and Gokul, followed by Mr. Panda and Hiten. And probably, I think, getting a little insight from them will set the ball rolling to get interesting ideas.
Sure, that'll be great. I wasn't aware, my bad, I wasn't aware of the presentations being in place. So
yeah, they have made some, they have made some very nice presentation. I would request Doug to start his start an insightful case study on one of the hospitals in abroad.
Great.
Doug, over to you, please.
Great, thank you. Let me share my screen. Okay, please tell me if you see my screen. My PowerPoint presentation.
Not as yet, Doug. I can't see it.
Okay. Let me make sure. Here we go.
Hi, Ruchi. How are you?
Hi, Hiten. Good. Oh, wow. Yes, we can see it, Doug.
Great. Okay. So I was asked to speak about a new hospital in the US, in New York City, and I was asked to focus on structural steel. And I'm going to try and, in talking about this project, I will also try to cover some of the other topics just mentioned. The project in particular is the NYU Medical Center in Manhattan, New York City. So first, I'll just give a little introduction to who Lara is and why we're giving this presentation, and talk to you a little bit about then the project. and then hope to answer some good questions. So we are a firm formed in the US a long time ago. We have offices throughout the world now. We provide services for many different types of projects, focusing on structural engineering. So whether it's new design, reviewing projects, and all different types of occupancies, we are involved and can do that. And the value of that to us is it gives us an enormous amount of insight and expertise into how to solve problems. Technology is important in structural engineering and in building construction. We try to be leaders in that in terms of computational design and coding, as well as building information modeling. So we have lots of skills in doing that. And we think that's important in leveraging new technology to provide better solutions and for us to be able to build and design efficiently. In terms of healthcare, me personally, I lead efforts for LERA over the last decade and a half. And whether it's a small little project somewhere in the country, some old facility in which we're just modifying a operating room, or if it's a brand new facility, we've been involved with it. And this gives us a lot of perspective. Projects are not just based in the United States. We have done projects overseas in China, one in Kazakhstan. And so we're always, given our international breadth of experience, being able to deal with healthcare throughout the world is something we're also quite strong in. And it also brings back expertise on how to possibly solve problems in the US. So NYU Langone Health is a private hospital, mainly in the New York City greater area. So let me talk about healthcare in New York City. New York City is a large community, like just like you have in India, say in Mumbai. And historically, this is a bird's eye view of the east side of Manhattan. Historically, hospitals rose along the east side of this island. And the reason it did was because it was somewhat isolated from the population centers, more on the interior, because historically hospitals were where people were sick. So we wanted to put all the sick people near the water. So we have what's known as Hospital Row on the east side of Manhattan. Circled in yellow is the site of the project I'm going to talk about. But this greater cluster of buildings is all hospital buildings for NYU Medical Center. Basically, it's a medical campus. For orientation, you may see in the upper right corner, the United Nations campus. Focusing more closely, you'll see in the lower right, there's some vacant land. Well, it wasn't really vacant. NYU had to demolish some buildings to make space for this new facility. But what you will notice is that there are a cluster of existing buildings and they want to be close together because adjacency in hospital construction is important. If you have operating rooms or imaging facilities in one building, often building new facilities adjacent to it is key so people can move back and forth. New York City is a dense urban environment, so you really don't have the opportunity to even spread out a little bit and have bridges to connect buildings. And I think this discussion goes to thinking about healthcare facilities in general. In many respects, the United States could represent the state of the art, but it's not necessarily perfect. But NYU, being a private institution, does have a lot of money. And they continue to invest that money in their facilities because that's the business of healthcare. Cutting edge technology and supporting physicians and their assistants. This was the campus over a decade ago. And you see it's completely laid out. And we're going to focus on the left side of the image. The Kimmel Pavilion is a brand new hospital that was built essentially adjacent to existing buildings. And that was key because this building in the middle, the Tisch Hospital, is NYU's main operating room platform, many floors of operating rooms. The Kimmel Pavilion, let me just go back, the Kimmel Pavilion contains 30 new operating rooms, 30 new ORs, and contains about 370 new bed rooms. It's a significant increase in capacity for the campus. Now the site is near the water. It's a very constrained site. And in urban environments, being able to build within these constraints is extremely important because institutions want to have the new buildings close to each other. We don't have the capability, if we're outside the city, we can take the lot next door. To give you an example of how constrained the site is, being close to the water means that with the revised flood guidelines, the whole site could practically flood. And these black lines shown here is where the latest FEMA, Federal Emergency Management Association flood maps indicate the water will go. So more complications with the site. But the most primary complication for this site, and the reason a new building wasn't built in this location is because there are significant tunnels in the ground below the site. These tunnels are train railway tunnels for Amtrak. These are passenger commuter trains that go from Queens and Long Island into Manhattan. So this is a main rush hour transportation mode. The tunnels are about 65 feet below ground. So whereas we're building this new facility above in structural steel, and I'll explain why in a second, we have to respect what's below it. And this is really where structural steel shows how powerful a structural solution it can be. This is a view looking toward the river. And what you see is about a third of the building is over tunnels. And we cannot provide, bare columns or foundations on these tunnels. These tunnels are probably in the order of 80 years old, and a lot of care is taken in dealing with them. So the concept is essentially that this building became a bridge. And what I'll say is that where this red truss is located is in the mid-height mechanical floor for the building. So the building has a 14-story patient tower on top of a 7-story podium. The podium has the operating rooms. The tower has the patient rooms. We effectively created the podium as a bridge over the tunnels. When the concept relatively simple, erect a steel truss over the tunnel zone. To erect the truss, we actually had to do some temporary shoring, and that's shown in green. And the columns shown in blue, first were in compression, and then through a series of unloading the temporary trusses at the base, they became hangers. So we're going through extraordinary efforts to make this site viable. To give you a little perspective from a structural design point of view, this simple hand sketch, which shows the tunnels as they exist on the site, the water is up here, illustrates that the core of the building, and when you have these stacked hospital facilities, you need a lot of elevators for patients, for doctors, for servicing. The core of the building had to be shifted over off-center significantly, and that's a penalty to the structural design that we had to overcome. The solution is illustrated in this 3D view with the core in blue, which is primarily a brace frame, bridge-like transfer trusses that are about 35 feet deep within that full-story mechanical floor. The trusses span north to south. Some are integrated into the core, and they allow us to span over these two tunnels. At the north end, these two tunnels are situated just slightly north of the building, but the building does cantilever out a little bit to avoid them. So we're affected by what's in the ground enormously. One other complication, and this is true in many cities, this big element here is a major sewer for the city that goes out to the East River. We also had to avoid that. We could not actually bear load on that sewer, so we needed temporary trusses, as I showed previously in green, above the sewer. Now, since this is a structural steel conference, we wanted to focus on steel a bit. Where warranted, steel can be extremely powerful because it allows us to erect long spans far more efficiently than in concrete. Whereas we had false work, we had shoring. That shoring was in relatively small pieces of steel that could be removed easily. And then the process of unloading the shores can be done fairly easily in steel with some jacking. The scale of the pieces for these main trusses, what's significant in locations? Some of these members are about 36 to 40 inches deep. You'll see here, this is a structural drawing of one of the principal trusses spanning from left to right. A key thing is detailing. In the United States, the use of a W14, 14 inches, about 360 millimeters, is the standard size for large-scale buildings. Where we used a built-up box section, we kept the width of it so that it could easily connect to W14 members. So having efficient, compact connections is key. Within the US market, the decision as to whether we should use high-strength bolts or field welding is an important one. The overwhelming preference would be to use field bolting. Weld in the shop, bolt in the field. And you see we have some of those types of connections. However, when the loads are extremely large, a partial penetration weld or complete joint penetration weld actually turn out to be more efficient. And during this process of design, we made estimates of where we thought connections should be bolted and where they should be welded. And by and large, when we sat down at the table with all the structural steel company bidding on the project, they agreed. So to show you actual photographs of what the steel work looks like, you see it there. As I mentioned before, the core was offset from the center of the building to dealing with the tunnels. In some locations, we did slope a column just because it was advantageous to do that. We had to avoid the tunnels in the ground. So that main member sloping is about 30 inches in scale, and it's about 20 inches wide. So here you see, if you follow that sloping member up, you see one of the trusses that we were looking at. You'll see the structural steel hanger columns extend down below it. In fact, if you look carefully at the bottom of the screen, you'll see temporary trusses that we used to erect the steel. In this view, down, I believe, 33rd Street in Manhattan, kind of gives you a sense of scale. The site is about 2 to 3 city blocks long. And the reason I've always liked this view is because it shows the density of the bridge and then how the columns are fairly thin down below, since they're primarily in tension. Here is a closer look at some of the built-up members as well as the W14s. Now, you may notice, and we're going to talk about this, that there's a special connection below the truss. The reason for this is because the trusses are located at the top of the podium that acts as a bridge, the trusses support the operating room floors. And in terms of healthcare facilities, this is the most critical space that can be provided. So there is a special hanger connection here. And that connection was designed and detailed such that we could allow, after complete erection, a jacking adjustment of the elevation of the hanging floors. Here you see me and my project manager, Joe Yaman, just so you get a sense of scale. This detail, as we originally conceived, was to allow for a jack to go in with some shims that could be taken out and some rods in tension, that we could move this bottom column up where the steel tolerances for the floors were not originally met. And the reason this is extremely important, despite the steel contractor boasting that they can install the steel according to tolerance, because an OR floor needs to have critical floor elevation tight tolerance. The equipment that goes in operating rooms, whether it's on the base or hung from the ceiling, is of paramount importance. And when floors are out of alignment, it just compounds the issues of installing all the medical equipment correctly. As realized, shown here in the steel contractor's Tekla model, they actually made a variation of our proposed detail, which was built. And here you see what these assemblies look like. It's essentially the same assembly over and over again. So we tried to use repetition for economy. Here you get a sense. This is curtain wall going in front of the podium, the operating room podium. And you see how these columns come down and then stop. And they're supported from this truss. To give you a sense of scale, the trusses span 100 feet. So it is essentially a bridge. Here you see a view from up above of the site. These two gray brick buildings, 1 and 2, are ventilation towers for the tunnels down below. So you can see how visually they're reflected on the site. This building here, which we're building right up against, is the Tisch Hospital. And so the new Kimmel Pavilion will connect to the base of the Tisch Hospital so doctors can go back and forth. In fact, if you go to the site now, you can walk into the hospital here, come out of an entrance on 34th Street, and you won't even notice that you're going between the two buildings. The integration is that connected. This is a view of the typical tower floors. We mentioned before that there were tunnels on the north side of the site as well, and so a strategy was employed to shift steel columns back from the edge and cantilever. This cantilever is on the order of 16 to 17 feet. And architecturally, in terms of clinical planning, the columns were positioned at the back of the patient room, integrated into where the bathrooms is. Where columns are located in healthcare buildings is often a very critical decision, and medical planners have a big say. In terms of structural steel, aside from the trusses, perhaps the scale of the members, the building is very typical for structural steel hospital construction in the United States. Not every hospital building is built in concrete, but a lot are. And the reasons for that are steel offers a lot of flexibility. During construction, if a MRI imaging equipment needs to change and you need to modify steel to deal with that during construction, or if 10, 20 years from now, operating room needs to change and we need to modify the steel, well, that's a lot easier to do than if we have reinforced concrete or post-tension concrete. So a lot of hospital administrators, facility division leaders actually prefer structural steel. It's regarded as the de facto material. Another important thing about hospitals is that the entrance, where the patient comes in, is important. Here you see a big opening. This is a grand atrium, which I'll show is reflected, is in this location here. Because when you arrive to the site, you don't want to be confused. You want to know where to enter. The trend for healthcare design in the United States over the last 20 years has been to focus more on the patient. Research has shown that where you provide an environment that the patient and their families feel more comfortable in, whether that's for a nice grand entrance or a nice bedroom. By the way, the 370 patient bedrooms in the tower of this building are single patient bedrooms. That is now the trend happening throughout the United States. It's going to take several decades. There are many older hospitals where you have two patients in a room, but research has shown that a single patient bedroom allows for patients to heal a lot quicker. And knowing that healthcare is a business, we're not just helping the patient, but bottom lines are important. That fact is actually hugely important, and that allows patients to have shorter stays in hospitals. And the trend with healthcare design is you come in, you get your procedure, and if you're inpatient, you stay in the hospital for the shortest time possible, and so that you can leave. And generally, people do prefer if they heal up enough such that they can leave and then continue their healing while at home, they are more comfortable. And so that's the logic of a lot of the new facilities that are coming online. Talked about the grand entrance atrium. The use of art to provide a reflective, contemplative place is also important. NYU has a arts program, but many of the leading institutions throughout the country do as well. And we helped to engineer this beautiful sculpture by Allison Schatz. The Kimmel Pavilion, the architects were Ennead Architects based in New York City in conjunction with MBBJ Architects. Just to add a little bit to some of the things we do, the artists, this piece of this sculpture is aluminum with acrylic on it, and the acrylic reflects different colors as the sun changes angles. And we had to do an enormous amount of computational engineering to optimize the shape of this piece. So there you see the bed towers and the podium, and you don't even know there's a tunnel below. So I hope I tried to address issues of structural steel as well as healthcare design. And I think one of the last things I wanted to impart is that an enormous amount of planning went into place. It is true, the United States has good standards for healthcare design, but those standards continue to evolve, and professionals, whether it's on the engineering or the architectural or the clinical side, do participate in the development of those standards to continue to improve them. With that, I'll open it to questions or give it back to the moderator.
Hey,
We'll take questions in. Yes, sir.
no,
You can take questions in the end after all the presentation.
Sounds good. I will stop sharing.
Sorry, Mr. Douglas, only one question.
Sure.
The partition walls and the outside walls are made of the framing technology or with bricks?
Yes, I mean, historically, for instance, the original Tisch Hospital, built in the early 1960s, had masonry partitions. All new healthcare buildings, I would say over the last 30, 40, maybe even 50 years, are using light gauge, thin metal stud partitions. And just as with steel for the building structure, those partitions can very easily be changed. And that's enormously powerful for future modifications. All these buildings we find are continually changing.
Okay, and the entire building is on the steel structure is painted with a fire-resistant paint for 2-3 hours or more.
Yes,
Like
the standard in the US is to use a spray-on fireproofing product. So there is no paint. We after the structural steel work is installed and the metal deck is installed and concrete is cast, a different trade contractor comes through and will curtain off large areas of a floor and using a spray gun, apply fireproofing.
Okay, thank you so much.
Where steel is exposed, say at the atrium, sometimes a special paint, fireproofing intumescent paint is used, but that's a lot more expensive. So it's more sparingly used.
Okay. Thanks. Yes, please.
With that, I will stop sharing. That's okay.
Yes, thank you. Thanks a lot, Doug. There are questions flooding in for you. So I'm sure Andrea is going to be sharing those with you and we can take them up at the end. I'll invite Mr. Subrat Panda now to share his presentation.
Yeah, good evening. And good morning to Doug and good evening to everybody. I thank you all for joining this webinar that we have been conducting over the last 2 months on basically as a knowledge dissemination webinar. Just is my screen visible?
Yes, sir.
Yes.
Thank you. Yeah. So I'll just run through you that what we do at JSPL and primarily in structural steel. So JSPL, we have 2 plants in India and 1 plant in Oman, and between the 3 of us we do about 10.6 million tons of steel, and we were the first producers of parallel flange beams in the country, and about 12 years back we started with the parallel flange beams, and of late Steel Authority of India has also joined into and started making some section of the parallel flange beams. We have been doing it for the last 13 years we have been producing parallel flange beams apart from the other steel that we do. We are primarily more of a infrastructure player, more of a long producer company, and we do a small bit of flat in terms of plates, but most of it is long products. So this is a product range that we do. We do TMT from 8 mm to, in fact, 6 mm to 40 mm. Wire rods we do from 5.5 mm to 20 mm, 25 mm. In plates, we can do plates up to 200 mm, starting from 6 mm. In rails, we manufacture both head-hardened rails as well as the normal track rails, which are used across the country. In structures, we do angles, channels, beams, parallel flange beams, W sections, UB sections, all the bearing plies, all those sections that we do. I'll come more into the details of structures later. Sheet piles we manufacture, which is basically used for the shore protection and embankment. Hot roll coils we do, currently we are doing from 1.6 mm to 25 mm, and we are the only producers of hot roll coil in the country who can do 3 meters wide hot roll coils. In rounds we do roll rounds as well as cast rounds. Roll rounds we do from 20 mm to 60 mm, and in case of cast rounds we are doing up to 350 mm cast rounds. And we also have a prefabricated shop wherein we do the higher fabrication. In roll sections, we up to 900 mm, we can give you the roll sections. And in the prefabricated sections, we can give you prefabricated sections up to 3 meters depth. So the structural product range that I was talking about is angles, channels, beams, columns, sheet piles, crane rails. In angles, we do up to 250 mm angles. In channels, we do up to 400 mm channels. In beams, we do up to 900 mm beams. And in beams, particularly to again reiterate that we are able to do W sections. In fact, when Doug was talking about the W sections, we do W sections from W6 to W36. Similarly, in UP, we do UB from 152 to 836, and in columns we do from column 152 mm to what would be W6 to columns up to 356 mm. And sheet piles, we have got one section that is 400 into 170, and crane rails which is used for the infrastructure construction. This is a fabrication facility which I was talking about, where we can do about 3 meters depth fabricated sections. And these are the facilities that we have at the fabricated mill. We have all these facilities which are available there, and we can do all complex structures in this fabrication. So now coming to the beams that we manufacture, we, as I told you, that we were the initial pioneers in the parallel flange beams in the country, and we do narrow parallel flange beams from 180 mm to 600 mm, or which is also equivalent to the IP series in the European standard. Then we do what is the W beams or wide parallel flange beams. This is from 160 to 160 to 900 into 300. We do universal beams from UB 152 to UB 610 is currently what we do, and we are adding certain more sections which are now ready for supplies. And then we also do UC 152 and UC 356. The basic difference between a parallel flange beam and a tapered beam is this. This is what the picture shows, that this is tapered and this is where the parallel flange beam comes. And the advantages of the parallel flange beams are that within the same notional width and depth, we can have a number of sectional ways and thereby optimize the section that optimize the steel design that we have. So this is one new development which has happened. This has happened on 29th of July. This was earlier, we had IS 2778 for the parallel flange beam sections and IS 808 for hot roll sections. And IS 808 was the design code. And since now IS 2778 has been merged into IS 808, and this is effective from 28th of August 2021. So a lot of design in parallel flange beams was getting affected because there was no design, because it was not covered in IS 808. So I think this helps as we move forward. And as I said, that in our quest to in our discussions with a lot of designers and a lot of architects, these are the sections that we have come across that would be required for, particularly for the commercial buildings and the hospital infrastructure. That is 406 into 150, 610 into 305, 750, IP 750, UB 762 and UB 838. And this is what we have done specifically for the building segment, that is UB 150 into 160. This is not a UB section. This you can say as a customized JSPL section. 450 into 160, 500 into 180 and 533 into 165. These are basically required for the 11 into 11 meters grids and the 10 into 10 meter grid that you have in a structural segment. So this is what we have already produced and we are now ready to supply. And the advantages of steel structure, Doug has already emphasized on it, that it has super quick to build, ease in expansion, ease in repair, faster erection, flexible. There's a wide range of the ready-made sections which are available. And most importantly today is that it can be taken down and it can be recycled and it can be put up again at some other place, which is not possible when it comes to RCC structures. The advantages of a JSPL beam versus a tapered beam, this is whatever, or what would be your parallel flange beam versus a tapered beam is primarily this, that there is no shear which happens at the bolt connection. And the other is that the connection length that is required is much lower when it comes to a parallel flange beam than when it comes to a tapered beam. And this is the primary reason for failure in the structures. And that is where the greatest advantage happens in a parallel flange beam, that you can, apart from the other advantage of design optimization in terms of multiple sectional weights. This is something that this shows that what is the buckling factor as it happens when you use a roll section and as you move to a cold form section. The buckling factor is lowest when it comes to a cold form section, and so a lot of times discussion is there that whether there would be, as the slenderness of the structure increases, this buckling factor keeps on reducing, and that is where the between a built-up section and a rolled section the differences comes into view. So if you consider the buckling factor of the rolled section and compared to a built-up section which can be welded from plates and made, then a rolled section will be approximately 5% higher than a built-up section. And this is the other factor that this is a graph that we have this is the blue line shows the price of hot rolled steel or flat products which is there currently, and orange line is the price of a roll section. So today a roll section price is almost about 5,000 to 7,000 rupees lower than a plate price, and then you use a plate to make a built-up section, and then the factors of safety which come into. So technically today we are about almost 10,000 rupees cheaper than a plate built-up section. So that is one of the other advantages that we have in a hot rolled in a roll section today. And the advantage today is that in a roll section the roll section prices will continue to, the flat product prices over the last 15 months have been strong, and they are expected to remain strong over the next 2 years. So this gap between the rolled and the flat product prices will continue, and it makes eminent sense to design in rolled sections rather than in doing a built-up section from a plate. Now, as far as the healthcare infrastructure is concerned, I think the Government of India recently announced a cover of 50,000 crores for ramping up the healthcare infrastructure in primarily Tier 2 and Tier 3 cities. And they have a loan guarantee scheme which would provide 75% coverage for new projects and 50% in the expansion mode. And the rate of interest is very attractive in this. But as we were seeing the reaction to this was that probably in 3 years a new healthcare infrastructure will not come up. So this is where that we have been trying to propagate this, that in case you use a rolled structural steel or a fabricated structural steel, it makes it much more easier to put up a project rather than going for an RCC sort of a project. So these are the healthcare buildings that wherein we have been involved currently. I'll just run it through you. So the advantages, as Doug has already said, and I'll only repeat that it is flexibility and adaptability, speed of construction, and minimize disruption, and service holds can be done much more easier. The other advantage that we as JSPL has been propagating is the use of high strength steel. That in India currently most of the steel designing is done in E250, whereas globally I think E350 is the standard base, or S355 as they call it, is the standard base, and then a lot of high strength steel is being designed. So the advantages of a high strength steel is this is what we have been that if you design something in E250 and you move to E350, the thumb rule is that if the increase in steel is increase in yield strength is about 10%, then the saving in steel is about 5%. So obviously, so if you move from E250 to E350, the increase in strength is about 40%, so the decrease in weight will be about 20% on a thumb rule basis. But there are certain ferroalloy costs which come into making this higher strength steel. So the overall saving in terms of cost will be about 15%, but the overall saving in terms of steel would be about 20%. Similarly, if you move to E410, the overall cost should be about, overall saving in steel should be about 32%, about 25% in terms of cost. In E450, it will be about 40% and about 30% in terms of cost. I will give you certain examples wherein we have used E450 steel in here. So these are the projects where we are specifically talking about E410 and E450. E350 is gradually becoming a standard today in India, but there are a lot of projects which have already been designed in E410 and E450. So this is E410 in Kolkata for the metro. Then in the Mumbai underground, Dogasoma and ITD cementation, they have done the underground tunnels with the E410 structures. E410, the whole of the steel bridge at Mahatma Gandhi Setu in Patna. This has been done in E410. A lot of smaller way bridges have trailers and those sort of applications have now moved to E410. Then E450 for the commercial buildings, the Spanish group in Hyderabad has been using this extensively, and they have come up with quite a few buildings now in exclusively designed in E450. The Dhirubhai Ambani Convention Center, which is opposite to Trident in BKC, this entire entire structure was designed in E450, and this was designed almost 7 years back. So it is not that it is recently that we are talking about E450. E450 has been getting used for quite. And E450 in the Central Vista project, wherein we used, there are two temporary buildings which came up in the Africa Avenue. So this also has used E450 grade of steels. Similarly, in a lot of these commercial projects that we have done, E450 in Mist Avenue and in Alphatum, and also in the sheet piles also, we have been using a lot of E410 grade of sheet piles. So this is the Ames Bilaspur. This again has been done with steel, wherein we have been supplying the steel from our fabrication unit at Chhattisgarh. And this is a multi-level car parking that we have done in Gangaram Hospital, again using steel. This is again a speed floor which we have used in Medanta Medicity here in Gurgaon, wherein the speed floors has been used. These are prefabricated steel joists that we manufacture from galvanized coils, and then they are used for the purpose of building without a prop. These are the towers wherein we have used commercial buildings wherein you have used steel. The Cybertrum project. This is the Central Vista project that I was talking about. This building has come up in a span of I think about 12 months, and we supplied the UB305 was what was used in this, and 450 grade plates. And this entire building has now come up in Africa Avenue in a span of 12 months. This is the Windsor IT building in here. These are the M3M in Gurgaon, where sheet piles. This is another unique product that we manufacture, and it is basically used for protecting the shores and protecting for water embankment. And currently we manufacture only one size, that is 400 into 170 mm with a thickness of 15.5 mm. This is the sheet pile which has been used at Nariman Point, and this recent cyclone that we had in Mumbai about 3 months back. I think this worked as a steel wall, and the entire site which was behind was totally protected without any issues because of these sheet piles. Similarly, we have used the sheet piles in NCC for rubber dam project in Gaya. We have used this in across the Hiten, and a lot of these projects are currently using sheet piles wherein they act as a retaining wall and as a shore protector. So that's all that I have. Thank you. Thank you so much.
Thank you very much, Subrat. We will continue in the same tempo. Over to Hiten for his insight on challenges and any projects that he feels that he would like to share with us.
Thank you, Ruchi. I'll just share my presentation. Can everyone see? Is the presentation visible?
Yes, sir.
Yes.
Yes, sir.
Thank you. Good evening, friends. First, let me thank MX Business Media for giving me this opportunity for sharing my presentation. I'm a director of Mahindra Consultants Private Limited. We are a mid-sized company with 300 people and about 8 to 9 offices all over India. It's a 70-year-old company started by my dad, and it's a family. My brother and my son and his son, all of us are structural engineers. A postgraduate from Michigan, UFM, and UCLA. Today, actually, I've been given an opportunity to talk on decoding steel with health engineering. I am not going to talk about any of our X projects, which we have already done. We have done quite a few hospital buildings where we have been able to do large cancer hospitals and either with steel and with concrete. I would like to basically start with introduction and general comments. Huge demand on temporary structures. The only solution, modular prefab structures. And then I'll go into talking about distinct advantages of steel structures over other technologies. I think Doug has also and Mr. Panda has already discussed, but I'll just go through it quickly and my concluding remarks. Desperate times require desperate measures. It's we are in an unprecedented situation with this corona pandemic, and instead of talking about one particular project, I'm going to be talking generally on the aspects of how, as an engineering company or as a structural engineers, and we can help in this issue which we have today. See, in India we have had a lot of problems regarding cancer hospitals were the demand at that time, and yet there is a huge demand. The government has tried different ways, and we have done a few cancer hospitals. One was in Nagpur, and one we were trying to do at Guwahati. But the speed and the demand is very high, and even the other facilities for diabetes centers are required. And with this corona coming up, it's basically we need to accelerate this whole effort of giving health facilities to everyone, to the nation and to the country. In effect, on every section of society in every country, this is a problem now, and we need a fast solution, and that's the need of the hour. Now the facilities which you require are hospitals, vaccination centers, quarantine centers, oxygen plants, like Mr. Sharma was talking about cryogenic tanks, and mini units, and also temporary units for emergency measures. And this type of facilities would be of varying sizes depending on the city, whether it's a one tier, first if it's a main like Bombay, Chennai, Delhi, or is it a two tier city, or it's a 3-tier city, or it's a village. So the type of facilities which need to be provided will have to be sized up depending on the demand. And time is very terribly short, and we need to have some sort of solution where we can provide quick installations at different places. And the only way I feel this can be done is to go for prefab structures. So we need to go for modular structures. Definitely some sort of a repetition also in structures where we can use semi-skilled laborers and provide the facilities as soon as possible, and also see that production, transportation, installations of the structures should be very fast in remote areas, and also in villages and in high altitude places. So I just give an example of how we could use steel quickly. In the present pandemic, there was a problem regarding oxygen, and we know that we had an issue in one of the hospitals in Powai. They needed an oxygen plant very fast, and we didn't have any space. So on the substation, existing there was a huge substation. We managed to provide steel transfer the load directly on the columns, on the external columns, and provide a quick solution for the oxygen plant. And they could commission it at record time, and the hospital was really in dire need of it, and the solution was given. So these are the type of solutions we can give even for the existing facilities which are available now in India. I'll quickly run through the distinct advantages of steel structures, which I think Doug and Mr. Panda has gone through. Basically, dead weight, there's a huge reduction. There's a flexibility in design. The beam depth sections and the headrooms available are less, so that we can get a higher headroom than the normal. And of course, we are talking about 420 MPa, 450 MPa, 355 MPa steel. So basically, with that, you can try to go for, you can get shorter sections with the composite deck action. Speed, no doubt, is very good, but provided I'll discuss a little later what needs to be taken care of if you need to also get that speed which you want in steel buildings. Number of agencies are much less than in structural or post-tension designs. Shuttering formwork is not required. The fit-ups can be done as soon as possible. Site restrictions, if there are, which are there in Bombay especially, we have a lot of restrictions in mega cities because of the congestion. Of course, the work can be done in the workshop, and the elements can be bought and erected on site. Labor requirement is much less. Quality of work is in control because we are doing it at the workshop. Creep and shrinkage, we don't, very less creep and shrinkage problems because of the concrete requirement is not too much. And rectification, modification is easy to handle by providing extra beams, propping up the with extra columns, with like reducing the grid of the columns also as and when required. And cost of construction, generally it's a misnomer. The cost is more, but if you finish the facility, if you close it faster, you can save a lot of time in commissioning. It gets commissioned faster, and that's the reason why it's being used for all the factories and other production areas. And the last of all, it is a very sustainable material. You have a green building, less of concrete is being used, so definitely it's an advantage. I'll just go on to quickly into how the space utilizations, junction details, which should be used if you want to go for quick construction and give flexibility to the architect or the user to work with. So as the spans can be large, you can literally have spans going from the core to the end of the building. Then you can have services which you can incorporate within the depth of the building. There are certain demands which we require from the manufacturers, which I'll speak in the end, which we need inputs from manufacturers to provide us, so we can go for we can design and give a quicker solution and erect it faster too. These decking systems which we are providing is the composite action. You have TR60, you have TR80 available, where you have a 2-hour fire rating, reduction in dead load because of so you can save on the foundations, and basically you can span to 3.9 to 4.8, so secondary members can be utilized, can be used less. The parallel activities, if not done, you will never get the speed of construction in steel. So this is a must. So you have different activities like deck laying, reinforcement, concreting, and floor finish fit outs should be simultaneously taken up at different levels if you want to achieve the speed. Now, this is a coordination which is required, which is a must. If you don't do this, your whole purpose of providing steel buildings is over. Okay, I mean, that's the advantage you need, and you can, if you do it in this way, parallel activities, then only you can get this advantage. And this is sometimes not done in the way it should be done, and that's why steel gets a bad name. Suddenly you say that a concrete building we have done, and then we have done a steel building. These guys took the same time. and this is a very important point which you need to keep in mind before you do planning and you go for construction of a steel building. Now, I just want to tell you regarding this composite decks. Now, there's also a deep deck system available now in India. We always talk about TR60, TR80. You have the 221 deep deck systems also, which is started manufacturing. We used to get it from Chorus. We have done one project in the Intercontinental Hotel at Marine Drive, where we use the slim deck system from UK. Deep deck, that's 225. Now, in that system, it's the Rolls-Royce system basically of steel decking, because you actually have to place the deck at the bottom flange of the member. And when you concrete it, you actually cover the full concrete, the beam, except for the bottom part of the flange. So you need not also have to fireproof the beams. Now, in order to do that, you require to have wide asymmetrical sections, which we don't get in India, or we'll have to make a built-up section with an added plate below. So this is what I would like to talk to the manufacturers, that internationally all these things are available, where we don't have it here in India. And we need these inputs from you all. Not only that, we need inventory so that we don't have to wait for the lead time. The only lead time we have is when we have basements in the building. The basements come up and we do the workshop, we get the material and we manufacture in the workshop and we get it. That's all. That's the only lead time we have, unless there is piling or the deep foundations where we require time to do that. So this is something which if we get, it's because in the hotel, we could equate to the flat slab in RCC. What happens is that you don't see any beams. So the client sometimes want a flat slab with clean services provided below. This is where you can provide it. Deep deck systems. Okay, so this is one thing I purposely got this, because the composite deck system is easily available. Everyone knows about this. Now I'd like to just talk about some of the detailing which is required to be done when you're designing. Like Doug mentioned, we're looking at bolted sections instead of plated sections or welded sections. We do a lot of weld in the workshop, and we try to see that at site you should have minimum welding, unless you have a cost issue. But generally in India, we try to avoid doing a lot of welding on site, because otherwise you have to have a third-party inspection agency and do all the testing, radiographic testing on site, which takes a little more time. This is the type of details which we can work on. We should work on when you're erecting huge loaded columns and trusses. Another thing is we find that fire becomes a big issue, because every time we look at, we talk about, we don't want to go to steel because we have a fire problem. Now the reason why I say that there are many different ways which we can tackle with fire. Generally, you have a 2R rating for as per the DC rules, NPC rules in India. You can do it by vermiculate spray, like what Doug was saying, as far as steel is concerned. But you can go for encased composite columns also. So we go for partially encased or fully encased, or we go for circular hollow sections, or we go for rectangle or square hollow sections, which are infilled. So we can do that. And with this, you probably don't need to go for fire, except you got to take care when you're designing hollow sections, that is square hollow sections or rectangle hollow sections and circular hollow sections. You may need to do a 1R fire rating, because sometimes it doesn't take care of the 2R fire rating when you have infill columns. You have fire board rated boards also. If you can clear it, you have that option. And the costliest option is intumescent paint. But generally, sometimes the architect requires to use their structural framework as their aesthetical element. For that, sometimes we are forced to use intumescent paint, because they want to show the member, they want to show the whole truss within their architectural intent. Another last and important point I would like to say is the erection. If the erection is not taken care of in a proper manner, the equipment required for erection is not provided on site, you will not get the speed which you want. So these are all the elements which are required to make, we keep on saying fast, fast. We sometimes cannot get fast if we don't use this. People take these things for granted, but I am seeing many sites where these things are not available. Now, cranes is a must, telescopic cranes, your mobile cranes, all these are a must on site. You got to use cherry pickers to take care of elements, which are far reaching the members, so that, you don't have manual labor with cranes taking, chain pulley systems. So all these things, on site you use, it takes a lot of time. Then you need deck riders. You can put in the decking as fast as possible. People manually lay the decks. Then you have the gun for the shear connectors. You need that. So you need a lot of equipment on site in order to facilitate to move all this. Now, another thing which I always say is that, normally, as I think Doug's structure had braced columns, and for the column cores, we generally use a lot of concrete shear walls in steel buildings. So that's a challenge, because that slows down the work, and the steel frame goes up. So what is the one way to solve the problem is that we provide steel columns at the ends and at the center of the shear wall. So what you do is you will end up creating a grid where the beams and the framework can go up right up, and the framework can go up right up to the terrace, and you can follow up with the shear wall concreting. The detailing is to be done accordingly. We have done it for one of the Nagpur cancer hospitals. It worked very well, and we could achieve the speed we wanted to achieve, not waiting for the shear wall to come up. And it went up all time, and it worked out very well. There we also had a challenge of we had a 12-meter cantilever span, where going up to 21 meters, but we use raker columns to circumvent that the cantilever issues. And concluding remarks are: we are handling a situation unearthed in the known to history. Fast and desperate solutions are required. Now, in India, this is where I like to appeal to the manufacturers. You have a company which is giving you we have been talking about it, steel manufacturing plates which are fire resistant. They've been talking about it since quite some time. We don't have quantity. We don't have the inventory available. We're just talking about it. If I want to design a factory, or I want to design a hospital, or I want to design, I don't have that available in volume. So what do I do? Then there's another manufacturing company. As normally what happens is that you have plates of sizes of 40 mm and above. The stresses have to be reduced. So quantity of steel goes up. Now there are manufacturers that provide the stresses remain the same till 100 mm thick. But you can literally, there's one manufacturer. I don't know about other manufacturers which give you the choice. So again, if you can maintain the stress like 450 MPa, whatever yield stress I can maintain, even if I go for an 80 mm thick plate, then I achieve the target for my tonnage. So I become more cost effective. So these are the issues which we need to, and as I was saying, wide flange sections, different sections. Now we are forced to do plated. We are forced to do plated sections. Why? As you had said that they are costlier. They are costlier. How do I bring it down? When I get inventory from y'all regarding different sections with 355, 450 MPa, not only for 250 MPa. So this is where we require inputs from y'all, and we'll be able to, like in America, they have varied sections. You can make the column sizing the same size. They can go up right up to the top with different thicknesses. So the center of gravity is maintained. So that facility we don't have. We have to manufacture plated sections to do that. So these are I took this opportunity because we need to do fast construction. We need inventory, and we need these inputs from manufacturers to give us this so that we can, take it out faster. So total system planning is required for success. Governments, architects, engineers, manufacturers need to pool resources and come out with implementable solutions for survival of mankind, and hoping that we can take this further. Thank you, everyone.
Thank you, Hiten. Oh, quite a few pain points coming out there. Huh? That was good. It's really nice. These are the platforms really where we need to get together. And we've been saying this time and again that design and construction is a more collaborative process. And it's not enough for a manufacturer to just kind of sell a product and then hope for the structural engineers to find solutions, and then architects to find solutions to cover up those structural issues, or hide them, or display them, be the design intent. And then it's up to the client then, finally, who has to live with the lifetime of the building in terms of trying to maintain it and make it look and function the way it was intended. So there are quite a few gaps. We do need to have a deeper understanding on where each, it's not that JSPL or any other steel manufacturer is trying to cut corners, it's just that their understanding is different from someone else's. So it's basically a link, a bridge which has to be developed between the various stakeholders and directly connected to the end user. And that's where I think the gap lies. And we need to have a focused approach on how to standardize solutions. It is the need of the hour. Healthcare will require a very quick turnaround time. And all technologies which will be available to mankind should be used in order to ensure that it gets developed. Now, I'll open the entire session to question and answers. We are in the question and answer session. So all participants, if they have questions, you can please put it in chat. And please address who you would like the question to be answered by, if it is specific. If not, then I'll give a chance in turn to all the panelists to answer the questions based on what they feel they can add. One question to everybody in India, it's like Hiten and probably Mr. Panda or even Gokul can address this. There was somebody who had sent a question out to MX Business Media regarding NDMA guidelines, where they made a statement that steel buildings are not permitted in earthquake zones beyond zone 2. So I tried, I had very little time. I had hardly an hour to browse through. I have not come across these guidelines as yet. So, but then it's been at least 7-8 years since I've designed a hospital last. So I looked at it and I couldn't see anywhere where it specifically mentioned that steel cannot be used in any zone, earthquake zones beyond zone 2. So if you guys can probably shed light on this, anybody?
This is a question which always comes around, and I would actually answer that by saying they mentioned steel buildings, but they have not mentioned composite buildings with concrete cores. Okay, because the whole resistance of lateral stability is on the concrete. Though I don't know why this is put up here in the clause, because everywhere around the world, they are all facilities and hospitals are steel buildings. Here we have an issue. There are a lot many issues in that for hospitals. So sometimes it becomes rather difficult to, like they've got instead of 2%, they're looking at a 4% lateral walls on both directions, and there are many other things which they add on. So you try to do as much as possible to reach that. But steel is not composite. Composite, as I feel, is different. We have concrete, and our lateral stability is on our concrete shear walls.
You're talking about composite or you're talking about hybrid?
I'm talking about composite with concrete.
Shear wall.
Yeah, core, basically.
Concrete core.
Yeah.
So anybody else, Gokul or Doug, I don't know, probably you haven't faced these issues back in the US, but I know post 9/11 for high-rise buildings, there was some codal change where it was mandatory to have concrete cores in buildings rather than just steel.
Well, you can build buildings in steel only or in concrete only. You can mix the two together. In terms of earthquake, high seismic zones, steel buildings are built all over the world. The key is the structural steel system. The connections have to have ductile elements in them because most codes want to dissipate the energy to reduce the force. Provided, so if India is looking for guidelines as to how to do higher zone buildings in steel, there's a lot of information, a lot of practice done throughout the world. So it's not impossible by any means and can be quite practical. Sure, a cost equation has to be looked at. In terms of high rise, practice in the US, high rises do not require concrete core. That is simply, that will fall out from the design of the building. There are requirements about, enhanced requirements about egress and perhaps protection, and then sometimes clients will come in and ask for certain types of systems or additional protections, but that becomes more discretionary.
It's not as per a code which mandates any concrete cores in US high-rise buildings.
No, that is not in the International Building Code, no. That would be prohibitive because cost for structure is very much market dependent. So for instance, we're talking about structural steel, and a large majority of the US will use steel. But there are markets where they want to use concrete even for office construction and hospital construction. And it's economics and it's trade preference. So the practice has to change based on what's historically being followed.
Okay. So basically both materials can be used in any earthquake zones. It's just a question of what is the preference based on the criteria and the ground realities around related to the project, right?
Correct.
Okay.
Right, correct. Like if you see, we have steel buildings all around the world in really high seismic zones. And I'm not really sure why NDMA doesn't permit it, but as Mr. Mahindra said, we can bypass it maybe by saying that it has a concrete core.
Great. And that's what, Hiten, when I had gone through it, I didn't have the opportunity to go through the NDMA guidelines right throughout, but I did notice pre-engineered buildings were prohibited. But again, that's a misnomer because everything is pre-engineered. They should call it portal-based or plate-based systems rather than say pre-engineered, because all steel buildings are pre-engineered for that matter. So that could have what is created a confusion in the minds of people, because nobody in their right minds can deny that steel cannot be ductile designed or ductile detailed to withstand the required lateral loads in earthquake.
Very true. Very true.
So great. I think that's fine. I can't see any other questions here. Avneet or Andrea, if you have any other questions which have been sent over to you, please can you put it through to the panelists?
So there are a few questions in the chat box.
Chat box I saw. Okay, there's a Q&A in which there are some.
Yes.
Okay, so there is one which is from Rajan Raina. He's requesting, he says, today when we are exporting a lot of fabricated structures across the globe, we still have to buy majority of sections from Europe and US. What are the plans of steel mills on this to be more competitive? I think, Subrat, this is directed at you.
Wow. As I said in the presentation, I think currently we are manufacturing almost the entire range of UB sections that is used. So starting from UB 152 to UB 838, almost everything we are manufacturing now. We are doing a lot of W sections that are used in the US and the Canada. And we are doing it from W6 to W36. The entire range almost leaving up some few sizes. We will be doing almost the entire range. In fact, we are currently in the process of exporting almost 15,000 tons of structures to Canada, and they are all W sections. And they are all in the lengths of 13 meters, 15 meters, 19 meters. So all sorts of combinations that is required, up to 56 feet, is what we are doing currently. We are doing the H-bearing plies, which is used a lot in Hong Kong and in US. So we are improving our range, because each of the sections, development of it costs about 7 crores if you want to do a particular section. So we are in the process of improving our range, but currently I think we should be able to almost cater to almost the entire range across the requirements of the customer.
What stress are these
And sir, what we are supplying to US is ASTM A65, which is equivalent to E450. ASTM A50 and ASTM A65, A60. So there are a lot of these solar applications wherein they are requiring the UB sections, the W sections. So there again A65 is what we are supplying.
Okay, there's another question which has been addressed to you, Subrat, is it suitable for constructing steel buildings in hilly and mountainous regions?
Sorry, I didn't get it. Is it suitable?
Is it suitable for constructing such structures in hilly and mountainous regions?
I think you will be able to answer that better, but as far as my knowledge goes, I think it makes more sense to do it in structures rather than to do it in RCC.
Yep.
And there are a lot of these hotels which are coming up in Manali and in Himachal, which are currently doing, and in fact they have been doing it traditionally with a lot of beams and a lot of structural sections.
Yeah, so setting up concrete infrastructure is not easy, and carrying the concrete which needs to be pumped in hilly regions actually starts posing a multiple challenge. It just keeps on exponentially increasing depending on the terrain. So it is obviously a lot more suitable. Steel structures are much lighter. It's just that, as Hiten was pointing out, that you need to have your logistics worked out pertaining to each site. Each site will have its own challenges, be it right in the heart of a city or on a hilltop with 60% gradient slopes, which we had faced. So it's always possible. You just need to factor in all the criteria and then plan for the systems, and then design them and detail them, and then have them erected. It goes pretty smoothly. So I think that is something which is okay. Now there are a lot of questions with regards to cost, so I just throw it out, and then finally we'll take a final question from Doug, which is addressed to him. So the first one is, of course, what is the thumb rule cost variation or cost comparison between steel structures to RCC?
That's a question for me.
No, that's not for you, Doug, but you can also add, we can get a US cost comparison too.
What I will say based on my international experience is that really does vary from market to market, and I would imagine it might also vary in India, but I'd like to hear from the rest of the panelists.
Yeah.
I think rather than cost, I think we should also look at the time. I mean, is it just about the cost or cost and time?
No, I think you can give an answer which you feel is relevant. We did a cost benefit analysis. I wouldn't call it just a cost analysis.
Right,
so cost benefit analysis, we put in all the criteria. It was done almost 10, 12 years back. And steel was prohibitively more expensive and the difference was quite a lot more than it is now. But even then it made sense. So it depends on what you are including in the overall cost comparison conversation, so to speak. But just a thumb rule cost differential between material to material and erection and whatever, and we don't look at the tangential costs, which are probably savings in terms of time, savings in terms of volume, and all that. We can look at it subsequently.
On a thumb rule basis, if you compare something with an RCC rebar 500, FE 500 grade and E250 grade of structures, the thumb rule basis would be that structural steel building would be about 20%, 18% costlier than a steel building. But the game changes when you move to this high strength structures. That when you move from E250 to E350, as I was also talking in my presentation, that the approximate saving in steel will be about 16% in terms of cost. Approximate saving in steel will be much higher, about 20%. But saving in cost would be about 15-16%. And that is when the difference keeps narrowing down substantially. And the way you move over from E350 to E410 and E450, then I think the steel makes much more eminent sense rather than RCC.
Great. Anybody else? Hiten, would you like to add to that?
Yeah, actually, basically it depends on the building. Normally how many basements you have, because the basements have to be done in concrete anyways. So there's a lag, like if you have a 2 basement, 3 basement, whether you're doing a steel building or an RCC building, the basement is the same. Now you gain speed as you go higher per slab. So the number of floors being more, you get a higher advantage. If it's a very short building or a 4 or 5 story building, and then you're looking at steel is going to be at least 25% costlier to 30%. Basically, what we have done an exercise, it should be in that range, because you got to look at the deck. You're not looking at the section at length. You're looking at the deck, the shear studs, there are a lot of other components which you need to take care of, and the erection and the contractor's profit and everything all put together, it works out to about 25 to 30%. But as you go taller and taller, the advantage becomes humongous. Okay, and then you'll end up, as you're saying, you can look at a rental income. Suppose I finish it 6 months in advance, then I break even, or I do this. So these are the things which you need to work out, as you said, the cost benefit analysis, depending on, and that's how, we found that doing steel buildings, especially where you have large when you have 1 lakh square feet, or you have very tall structures, like, we have done buildings where our footprint itself is about 80,000 square feet. And the building itself is about, say about 1.5 million square feet. So there the steel became, like in Hyderabad, those buildings, with Phoenix, where we got a good advantage when we did steel from speed point of view.
I think Phoenix, they were able to do at a consumption of about 5.2, 5.6 kgs per.
Yeah.
Just to add in to what Hiten sir added, I mean, along with the cost, I think what we significantly also found beneficial was steel buildings are much lighter, right? So the effect, and lighter means the impact on the foundations. There's the loads on the foundation are lesser, the lateral loads are lesser. So we can also see a huge impact on the foundation quantities and the wall quantities that usually come in. I mean, in a project we saw, for a high-rise building, at least we could have, we reduced the wall thickness by around 15 to 20% by using a composite gravity system because of the reduction in the mass. So that is again an cost which, reduction in cost which cannot be captured in a material quantity, comparison, right?
Yeah, I know. So thank you. Thanks for that insight, Gokul. The thing is, there have been, just to give you a feedback, I smiled when you said about, lighter weight and impact on the concrete. You need lesser concrete in the foundations. I had a client who told me, no, I want the foundation designed as per whatever it would have been in case of a concrete building, but I want to build it out of steel because I have unconsumed FSI. I'm not getting permission to go more than 30 meters high, beyond 30 meters. So I want to consume that FSI later. At some stage, it should be able to come out. So, there are many considerations. I've given you an absolutely, tangential example, but yes, that is the bottom line, that we need to understand every site and every project in its actual context. And sometimes the most ridiculous factors start impacting the design decisions, but they are still relevant. So great, that'll be nice. I'll take one last question with Doug, and they're talking about, the question is addressed to Doug specifically, which is how have you taken care of vibration, which is the tunnel vibration transmitted to the building?
Well, actually, the tunnels are so far away that the effect on the floors with medical equipment is, was minimal, was non-existent.
Oh, okay.
But we did, vibrations in healthcare facilities is a really important topic that I didn't even touch on. Floor systems have, let me backtrack a little bit. In the United States, there are code requirements or guideline requirements for meeting vibration levels for floor systems in hospitals, whether it be patient rooms or, more importantly, operating imaging rooms. And that will influence the quantity and the depth of steel significantly. There'll be a measurable difference between an office building and a hospital building in terms of what the steel is. And that's to satisfy, to ensure that the floors, when people walk, do not vibrate too much that will force the medical equipment, whether it's operating or imaging, to go offline. I don't know what the practice is in terms of the state-of-the-art equipment in India, but I suspect that you'll be approaching those type of considerations as well. So that's a whole other discussion I could have talked about. In terms of the tunnels are about at least 65 feet in the ground. So that vibration really dissipates. It was not a factor.
Great. And what have you used for, floors are obviously concrete deck floors. And what about the walls? I did hear you say that they were panel walls.
Well, the walls would be made out of cold form metal stud construction with sheetrock.
Okay.
Now, one thing that's interesting in the US that's happening is the use of the true use of prefabricated systems. The Kimmel Hospital had prefabricated bathroom pods. So you had a bathroom, say 10 by 10 feet, that was wholly prefabricated, put on a truck, lifted up in a hoist, and then rolled on the floor, and then put in its depressed area. Other hospitals are considering the use of prefabricating, or have actually used prefabricated mechanical systems. That is, you build sort of a light gauge structure that holds the ducts, the conduit, the trays. You build them in long segments, and you hoist them up and stick them in and lift them up into the ceiling, and then you connect them. And that thinking is becoming more and more powerful to just leverage costs, reduce costs on projects.
Great. Okay, I don't see any further questions except for, there's one. This is to you, Hiten. It's addressed saying that in India, most stringent systems on welding, example, producing qualified welders. Right now, it is seen that the weld qualities are compromised more often than not. So what do you think about the detailing? He is thank you for bringing this issue up, but I can't understand the question really. Is he saying that bolted systems are far better than welded?
No. I think what he means is that basically, even if you're doing welding at the shop, I forgot to mention this part. This is also a very important part in the fabrication, is that we have a third-party agency that is a testing agency which is required for all our jobs. So with that, you make a quality assurance plan, you have a welding procedure setting up and everything. So that is all documented. We have someone in place always for every project. There's a third-party inspection agency which goes to the factory, to the shop floor, and gets all the weldings tested. If you need to do a welding test on site also, we get it tested. So there's a complete quality assurance plan. So that is a must for any project, and that should not be compromised. I mean, in concrete buildings, everyone does their cube tests and the routine, but in steel buildings, they miss out on all these, and this is like as routine as doing a cube test. It should be that way. So this is done on all major jobs. Wherever we have done, even if we have done a retrofitting job like we did in Wankhede Stadium, there was a third-party inspection agency for every welding and you do a bolted joints also, but you do welding. You do both in any fabrication project and any steel project. So you need to have a third-party inspection agency.
Great. The last question, I guess, now is which softwares are the best to provide connection designs as close to real connections at site?
Gokul can answer that.
Yeah, Gokul, you can have a go.
Yeah, primarily it has been Tekla right now, because that's I mean, it has a whole varied types of connections that can be actually programmed in and looked at any class detection. So the kind of services that Tekla is offering is right now at like one of the best right now, but there are again a few more which are coming in. But if you want me to just name one, I think Tekla is there, and I believe everyone knows about it.
Yeah, being an architect, the first thing that came into my mind was Tekla being the gold standard. But then I'm not the person who's qualified to answering that question. So I thought that you and Hiten could do so. So Tekla, both of you agree that it's Tekla which is the best so far.
Yeah, perfect. Yeah, that's true. Tekla is and we have been using it, and it's really helped us in providing connection details, which are required now at with the connection. So Tekla, I think, is the best, in my opinion.
So I am quite done with this. I haven't seen any further questions in here. In case, Avneet, you have anything to be asked or addressed to the panel specifically, please let me know, or you could take it up. Andrea, it's same with you. Otherwise, thank you very much, gentlemen. It has been a pleasure being here and looking at something which is very close to every society's requirement at large. Healthcare is something which is a backbone. It's as important as roads and waterways and stuff like that, but it's not so obvious till such time that you have an extraneous situation such as what's the pandemic which has hit the entire world. And no longer can we think, countries can afford to think in isolation. We need to think at a global level. It is mankind's future which is at stake. It's not any individual country's future now. So with that, thank you very much, gentlemen. Avneet, I hand the proceedings over to you for you to conclude.
Thank you so much, Ruchiji. It was a very fantastic presentations today and insight on a very niche sector, which we have never taken up before. So I think healthcare is one of the most key element after this pandemic. Everybody has realized that. And I'm glad we managed to get Doug on board, who gave his international perspective. There are a lot of clarification we got on the guidelines, which have been always been kind of discussed in in a closed door, and we kind of opened it up. That most importantly for seismic zone 2, 3, 4, 3, 4, and 5, I think we can definitely use steel. So there was a lot of myths that we have busted today. I'm glad we had such a fantastic panel with us who gave us such an elaborative insight on healthcare infrastructure. Thank you all for joining. In fact, it was a pleasure to have you all on.
Thank you. And on behalf of GSPL also, I thank all of you for joining. Thanks. Thank you so much.
Thank you. Thank you.
Thank
Thank
you.
you, everyone.
Thank you so much.